Hello, everyone, and welcome to Crowded Beaker. In your chemistry travels, you're going to see a lot of chemical compounds. They'll have a lot of different properties and they'll do a lot of really cool things. But at some point, we have to be able to express what compound we're using by calling it a name and writing a chemical formula for it. You're probably aware by now that chemicals, uh, pure compounds, have definite chemical formulas with little letters for the elements and the little subscripts that go with them. Today, we're going to be focusing on writing some of those. Some chemical compounds form little groups of atoms that are covalently bonded, and they can go around and travel the universe as a group, exploring, seeing what's out there. Other compounds, other compounds may create crystal structures, sort of like this one, which kind of go on in all directions and contain billions and billions of atoms. And these are what we call ionic compounds, and we're going to be focusing on ionic compounds in this episode. And how do we represent it, and how could we write the formula for something like this? So let's get started. In this video, we're going to be talking about three specific things. One, what are ions and how are they formed? Two, what are the four types of ions? And three, how do we put them together to make a chemical formula and represent that? So let's get into it. First of all, ions is the general term that we use for anything that has a charge. Okay? And ions are formed when an atom gains or loses electrons. You're probably aware by now that electrons on the outside of the atom can be given away or they can be taken from another atom. Now, a fun term that we like to use is called oxidation, which is the loss of electrons. And when something loses an electron, the atom becomes positive because now it has more protons than it has electrons, and so the protons win and you get a positive charge. Reduction occurs when there's a gain of electrons. I know, it's a weird term, but go with me on it. Electrons are gained, now the atom becomes negative or an anion because it has now gained extra electrons, which are negatively charged. Look at a couple quick examples. First of all, if we were to take an atom of lithium, lithium has 3 protons and 3 electrons to start, and it has a certain size. And lithium says, I would really like to be more like helium, with those 2 electrons and just the outer shell that's filled. And so it gives one away, and we end up with a positive 1 charge because now it has 3 protons and 2 electrons, an imbalance. Fluorine, on the other hand, is happy to take that electron and add it to the 9 that it already has. It ends up with 10, so it actually becomes isoelectronic with neon. And then you have a negative 1 charge because now it's got an extra electron. And I've just got a couple of fun little review slides for you showing their electron configurations and how they change. 1s2, 2s1, and then 1s2 is what we get with the positive charge. Note that the size of the ions changes, and the cations get smaller because they're losing electrons, and the anions are getting bigger because they are gaining electrons, and those electrons repel each other and they get a little far away. And once we get to the formation of ions, this is where the fun begins. So ions attract each other when they're oppositely charged. So a cation finds an anion, they stick together like little magnets. But here's the thing. They don't stick together in just one direction. They don't make one pair and then they're happy and they're fine. Hey, let's pair up and go around the universe looking at things. Instead, they attract in all directions. So you end up with a situation where a cation attracts to all kinds of anions around it. Those anions in turn attract to cations around it, and the process repeats and repeats and repeats in all directions. So you get these crystal lattice structures that are just, ginormous on the atomic scale, containing maybe billions and trillions and who knows how many atoms. And it adds up to a shape of an actual crystal that you can actually see. Here's an actual crystal of this sodium chloride. It has the same right angles as my model because that's the way the ions stack together. And so this is a really cool, it's one of my favorites, my little salt right there. And so we need to be able to write formulas for them. But how do we do that when there's gazillions of ions in there? How do we simplify that? All right, that's what we're going to get into today. And now we're going to move into part 2 on the types of ions. This is a document that I made. Feel free to borrow it. It just made sense to me. And It basically says, okay, if we're going to do an ionic compound, we need to have some sort of cation, some sort of positive charged thing, and some sort of anion. Okay, now there are two types of cations and two types of anions. So that actually ends up in four different types, four different subcategories of ionic compound. And we're going to do each one in a separate video. We might have a metal ion and monatomic anion. That's what we're going to do today. The metal ion, actually, let's talk about it. So the metal ion is for a typical metal ion that might only have one charge, like sodium. Sodium's always +1, or lithium is +1, and aluminum is +3. Okay, and when you represent that, you would just name that metal, like sodium ion, aluminum ion. On the anion side, those things on the right-hand side of the periodic table, like chlorine, oxygen, and iodine, they will gain electrons. And because we want to show them that they're in a compound, we're always going to write the metal first and the nonmetal next. So we change the ending to represent it that it's in a compound. And we're going to call those with the ending IDE, chloride, oxide, iodide. Now, I got to warn you off about the transition elements. They decided a long time ago, they had a meeting and they said to each other, hey, you know what? We don't want to be like those, boring sodiums and things. We want to make life difficult for chemists. So we're going to have more than one possible charge in many situations. So like iron could be a +2 or +3. How are we going to deal with that? So those get their own category. Polyatomic ions, those are groups of atoms that have a charge. And so we're going to deal with those separately. And you can mix and match any two combinations. Any one of these two with any one of these two gives us four possible combinations. And that makes it so we have to do like 4 little videos on that. All right, first let's talk about the regular metal ions like group 1A, 2A, and 3A. Or nowadays it's 1A, 2A, and 13. That's aluminum's column. And they only have one possible charge, +1, +2, +3, and that's typical of the column that they're in. And then we can write their formulas there and the numbers of protons and electrons that they have. The anions down here in groups 15, 16, and 17, that's the old version here, have negative charges because they get electrons. +3 for this column, +2 for that column, +1 for that column. And so we have -3, -2, -1 on those. All right, the other transition metal ions, just a reminder that they can make more than one possible charge. And when we get to it, we're going to use Roman numerals to represent them. That'll be in a separate episode. In general, though, you can actually see that things that are in the same column tend to have the same charge in a lot of situations. So everything here is +1, everything here is +2, and so on. All right, last thing before we start writing some formulas. Polyatomic ions are those groups of atoms that have charges with them. And so they have names that usually end in ate or ite. We'll practice that when we get to it. But they have formulas. You'll see 2 elements, 2 or more elements with charges attached to the whole thing. And those are polyatomic, meaning many atoms. All right, so again, we're going to be focusing right here in the top section today. With the regular metals, keep it simple, and the regular monatomic ions, we'll get to those later. All right, how are we going to write the formulas for something that looks as crazy as this? Well, we're going to try to get the lowest terms ratio of these ions. Yes, there's millions of them, but we don't want to write that. So what we're going to do is use their charges. We're going to determine the charge on each ion. We're going to use as many as we need to make the total charge 0. That is the key. The total charge for an ionic compound has to add up to 0. And so if we can make it do that, using however many we need, we're going to do it, and we're going to write the formula from that. And we're going to add subscripts to show how many you need. I'll do a couple examples before we pause the video. First, let's do potassium fluoride. And you're going to want to get yourself a chart of ions. There's gazillions of those on the internet as well. This one shows me that potassium is +1 and fluoride is -1. We already saw that over there. So let's write the formula for it. I know it's going to need potassium, okay, and that's a plus. I know it needs fluorine, and that's a minus. Now, would you agree, hopefully you would, that if you took a +1 and a -1 and added it up, you would get 0? On a number line, that would be 0. So that's what we're going to do. We're just going to need one of each of them, and they magically balance in a 1-to-1 ratio because the one cancels out the other one. That changes for something like calcium chloride. Calcium is in column 2, and so it needs a +2 charge. All right, so we'll write it down. Just go ahead and do this. You'll use up some paper, and that's fine. But chloride happens to be in the same column as fluoride, so it's -1. Now, you probably agree that a +2 and a -1 do not add up to 0. So what are we going to do? Well, I can't change those charges. That's what they have. But what I can do is add some more. All right, so what happens? There's no reason why the calcium can't just, hook up with one chlorine. What if it decides it collects 2 chlorines? It's going to hang out with 2 chlorines at the same time. And what that gives us is a 2 positive charge and a total of -2 charge, because now we got 2 -1s, which will cancel the 1 +2. And my chemical formula then is CaCl2, because I used 2 of the chlorines to balance that out. Let's do a couple more, and then we'll have our pause the video moments. So let's do lithium sulfide. Lithium sulfide, we've already seen, can be a +1 charge only. And sulfide happens to be over here in the same column as oxygen. Things in that column tend to be -2, so that's a 2- charge. And again, we have a situation where a +1 and a -2 do not add up to 0. So I need to do something, and that means I can add one or the other to make it equal to 0. And because there's fewer positive charges than negative charges, I'm going to add another lithium, which gives me a total of 2 positives and 2 negatives. So my formula that I should write is lithium with a 2, sulfide with a 1, and Li2S is my formula for that one. Again, keep in mind that the lithium sulfide crystal has gazillions of these, but they are in a 2-to-1 ratio. For every 2 lithiums, there's 1 sulfide, and that's what we're trying to go for. All right, let's kick it up a notch with aluminum chloride. Aluminum happens to be a +3. We've seen that. And oxide is in the same column as sulfide, and it has 2- charge. Okay, word of note, you can write it as a +3 or a 3+. It doesn't matter unless it really matters to somebody you know. But for me, I always say it doesn't matter. It's just, Okay, so here we go. 3 and a 2 are not going to add up to 0. I need more of the negatives, so I'm going to add another oxygen. But here, oh man, I got another problem. Now I've got +3 and -4. That still doesn't match. So, gosh, what am I supposed to do now? Well, now I need more positives, so I can only use the +3s. Let's add another one. And now I've got +6 and -4. My spidey sense is tingling a little. And I'm thinking, oh, wow, I'm actually getting to the point where if I add another one of these, I get a total of +6 and a -6. Sorry about that. And yes, the numbers got a little bit bigger, but they do balance. And that's the key. If I can make them 0, I'm done, with the exception of just writing the chemical formula. But in this case, I needed 2 aluminums and 3 oxygens to actually do it. Okay? And yes, each one of them gets a subscript in this case. Now, some of your spidey senses may be starting to tingle a little bit, and you're like, wait a minute, I feel like I'm using the same numbers over and over again. And one little shortcut that you can learn is that if you know the charges, 3 and a 2, and you reverse them, they become the subscripts in your formula. So a 3 and a 2 become a 2 and a 3 by just swapping them. If you look at our other examples, that happened as well. A 2 and a 1 became a 1 and a 2, and so on. So it's a quick, easy way to do that. Again, you want to make sure, though, that this gets reduced. So if you ended up with a 2 and a 4, you'd reduce it to a 1 and a 2, because you can just put it in lowest terms that way. We'll see some of those later. All right, pause the video. I came up with 2 easy ones, and I'd like you to pause the video, take a moment, and see if you can write the correct formulas for those. I'll see you back here in a couple seconds. All right, and if you came up with BaBr2, because barium's +2 and that's -1, congratulations. And if you came up with a Li3N, because lithium is +1, nitrogen is -3, and that would be its chemical formula. So hopefully we're getting a good start on writing ionic compound formulas. We've spent our time at the top of this chart. We're going to start working with the first diagonal, transition metals, next time. Then we'll do monatomic ions again. Then we'll add in the polyatomic ions for both of them, and we should be ready to rock and roll after that. I hope you found this helpful, and as always, if you have questions, you can send them to me in the comments or directly. And in the meantime, happy studying and have a great day.